About object-oriented programming. I promise I will keep the presentation part really short. I just want to do a quick overview of what we're going to talk about, and then we're going to dive into some code, and hopefully you guys get something out of this. I'll do a quick little introduction to me. We're going to look at object-oriented programming, how it's implemented in CODESYS. I'm actually going to talk about a couple different ways to implement it. And hopefully a new way that maybe some of you hadn't seen before. That's kind of my plan here anyway. I'm going to talk about standardizing a program, and we'll dive into that a little bit more. And then, of course, the live demo, and we'll actually see this in operation. So first of all, as Chris said, I've been around forever. Been doing IEC 61131 programming for a long time. Specifically with CODESYS on the Bedrock automation platform. By the way, you'll see the Bedrock IDE in my live demo here. Looks a lot like CODESYS, as you'll see. I also do SCADA programming and Windows development and training as well. Most recently, I spend most of my time in the water, wastewater industry. The example I'm going to show you today is actually a pump station from a water facility, but I also dab in oil and gas and building automation as well, where I need to anyway. All right, that's me. Now, object-oriented programming. So last year, Tech Talk 2021, Gary Pratt did a great overview of object-oriented programming. And if you haven't seen that, it is on their YouTube channel. That link is provided there. I think if you just search for CODESYS object-oriented programming anyway, you'll find it. Or as Gary calls it, object-oriented industrial programming, OOIP. But you know, the general idea is to create reusable pieces of code. And Alex actually gave you a great example of that in taking his program, making it a function block, and reusing that program over and over again, which is kind of what I'm showing down below. You know, in the old traditional days, we had a separate program for each item or each pump. And we called each program, we copied and pasted, we renamed things constantly. And the whole idea of object-oriented programming is to create a single program and then call that program multiple times, passing in separate data or setting up separate data for each one of those objects. And that's really what it boils down to for me anyway. Object-oriented programming is creating these reusable pieces that you can use over and over again, and both simplify your program, standardize your program, and these reusable pieces of code you've tested over and over again. You know they work. You don't have to worry about retesting them every single time you use them, and that's really where things come together for me. Now, how is this implemented in CODESYS? So typically, function blocks are how this is implemented. You create a data structure or a set of variables, instance that data structure or function block, develop the function block, you know, and just like Alex did, you instance that function block, give it a name, and then you create a program to execute that function block multiple times. And most of the time you're passing input data, and then you're grabbing output data from that function block and passing that on to use it somewhere else to drive your outputs or whatever that happens to be doing. And that works great. I've started using another method where I use data structures. And I'll introduce you to data structures when I get into the live demo, talk about that a little bit more. But instead of using a function block, what I've started doing is using the var in out feature in my program. So I create a data structure, create a program, and then simply call that program, passing my data structure into that program. all of the data I need for that particular object is contained in that data structure. There's a couple advantages that this gives me. There's also some disadvantages that we'll talk about too. But some of the advantages, I can really organize my data structure or my global variables exactly how I want them. I can actually build kind of a tree to organize all of my data the way I want. And then I call these programs, passing that data to these programs over and over and over again, and standardize things. I hope I did a good job explaining that, but it will definitely become more clear when we get into the program and show you how that's actually implemented and used. Now, one of the trade-offs I will talk about, and we'll see when we get into the code, is troubleshooting. With function blocks, troubleshooting is really easy. You can open that instance of that function block, see everything that's there. When you're calling a program over and over and over again, it can be kind of difficult to get to the actual instance of that program that you want to see, or get to the instance of that data structure. And there's some tricks there to help with that as well. So we'll talk about that a little bit. Now, another approach I've started adopting, and I can't take credit for this. A friend of mine at Golden Automation in Golden, Colorado, actually, is the one that showed me this type of standardized programming. And I really latched onto it and took his idea and implemented it in CODESYS and the Bedrock IDE. But it really works well in the water industry. I don't know how it will transfer to your industry, but hopefully it kind of gives you some ideas and maybe gets you thinking. What we came up with in the water industry, there's really three types of devices that we interact with in the outside world. We have an analog instrument. That's typically, say, a flow meter or a pressure instrument or water quality instrument or something like that, something giving me an analog value from the outside world. And of course, that could be a 4 to 20 signal. It could be coming from an Ethernet IP device or a HART device or whatever. It doesn't matter where it's coming from. Either way, it's an analog instrument that's giving me some data. So that's the first type. And then we have a digital instrument of some kind, typically a switch. You know, in the water world, it's water on floor, or maybe an intrusion switch to say that somebody opened the door or something like that. Just an on-off digital instrument, right? And then lastly, we have equipment. Now, equipment is pretty broad. This is valves, pumps, VFDs, a generator, things like that. Anything that we control, any kind of moving object. So starting and stopping a VFD or moving a valve, something like that. So what we did was we created standard data structures for these three types. So for instance, an analog instrument, you almost always want to alarm on that, right? So why not just build a handful of alarms into that analog instrument, and you can determine whether you want to use them or not in the code, but they will always be there. Later on, if you need them, you can enable them and use them as you see fit. So the advantage here is we have standard code that we call for all three data types. So for an analog instrument, I call some standard code. That takes care of all of my alarming, anything that's associated with the analog instrument that's common to every analog device. So I instance that particular data type, my analog instrument. I call the standard code. And then if I'm doing anything with my process with that, I pass that data structure onto my process, and I can use it in the actual process code that's actually doing something. Same thing for the digital instrument, same thing for the equipment. So it really streamlines the code, gets all of that standard code off to the side, and takes care of all of that standard stuff that you have to do for every single piece of instrument or every device that you connect to. Takes care of all of that standard code, and then you can focus on the important stuff, that process code and what this particular site is actually doing. Notice that we do separate out the devices. the IO. So that's kind of a separate piece where we're pulling in all of that device information, wherever it's coming from, hardwired IO, like I said, or hard or Modbus or whatever. We pull all of that in, and then we have a separate piece of code that maps that hard device IO to our data structures, kind of separates that in the code. So, and we'll talk about that as we go here. So just to give you a quick overview of what these instruments look like, as I said, the analog instrument is really for any analog type data. At least for the water industry, we include 6 alarms, and they're configurable for high or low. Typically, we do 3 highs, 3 lows. And as I said, you may not use all of those. You just enable the ones you want for that particular object and use those. Of course, those alarms can also be used in the process code. So take a tank level, for instance. You could use one of those alarms to indicate that my tank is getting high and I need to start my pump. So they're not necessarily just alarms either. They can be used as process type events as well. We also include device failure and warning alarms. So if we've lost communications with the device, or the device itself has some kind of a warning to let us know something's not right. So we just include that. So that's always there and available. If it happens to be, say, a flow, most of the time, my water industry customers anyway want to accumulate that flow. They want to have a total for the day, a total for the month, and then probably another total that they can run based off, say, a batch kind of situation, or manually start and stop it, things like that. So in the analog instrument, we included that accumulation and built it in. Again, something you can enable and disable depending on the type of instrument. We also included 2 additional outputs, and that's for unit conversions. So they, in some places, they might want to see the flow in gallons per minute. In other places, they might want millions of gallons per day, something like that. So we just built in 2 additional outputs that can do unit conversion, and built that into the instrument. And then lastly, any other features that might be common to use with any analog instrument. For instance, value clamping, if you want to clamp the bottom or top, things like that. Putting it on calibration hold, which is pretty common in the water industry. If they have to calibrate an instrument, they can just tell it to hold, stay where it is for right now. I'm going to go calibrate this instrument, make sure it's all good. And then when I'm done, I can take it out of calibration hold and put it back. And then if the device fails, what should I do with the current value? So if I sense that this device is no longer talking, what should I do with this value? Should I leave it where it is? Should I go to a predefined value of some kind? Or should I just go ahead and pass the value through, even though it says that it's failed? So all of those features we just built into this analog instrument and made it available to every analog device that we connect to. Now, digital instruments, pretty much the same, except a lot simpler, right? All we have is digital data on or off. We have 1 alarm because most of the time this digital instrument is being used for some kind of process alarm. Like I said, maybe it's a high level in a tank or water on floor or whatever. Again, we have device failure and warning alarms, and then we have our calibration hold and device hold settings as well in the digital instrument. Now, the equipment object gets a little more involved because this is a controlled device of some kind, a VFD or a valve or something like that. What we decided to do in our applications anyway is create 40 total digital alarms that are available for the equipment. And we grouped those. We have 10 failure alarms, 10 not ready alarms, 10 interlock, and 10 warning. That allows us to create some grouped alarm tags as well. So for instance, any failure alarm active, I can have 1 bit that turns on if one of my 10 failure alarms is on. And then of course I can use that for shutdown purposes or things like that. And, you know, we arbitrarily kind of set these because this works for this industry, but they could really be grouped however, and used however. Typically, the way we do it is a failure alarm is something coming from that device. So we've lost communications with it, or it's indicating that it has a high temperature or something like that. Not ready means that the handoff auto switch is not in auto, or something like that, or the device itself is telling us that it's not ready to run. Interlock alarms we typically use in the process side. So there's some other device in the system that's telling us that this device can't run right now. Maybe it's a valve on the downstream side of our pump that has failed. So we interlock our pump because that valve has failed, things like that. And then of course the warning section is just to tell us, hey, something's not quite right here, you might want to look at it, kind of thing. So that's how we broke that up. Now on equipment, everybody always wants statistics, start counters, run times, and typically runtime is grouped by current day runtime, previous day runtime, current month, previous month, things like that. Availability as well. So anytime this piece of equipment is not available, we have counters there to count how long it's been available and not available, things like that. And then lastly, what we did in the equipment group is we created these data groups that just have a whole bunch of data in them. There's just a bunch of reals, booleans, double integers, and strings. And they're used for passing data in and out of the equipment. And we also grouped these into 4 different groups. We have an HMI group, which is specifically for the HMI interaction with the device. We have a PLC group, which is for passing data inside of the PLC between different objects. And then we have a raw group specifically for mapping that device IO into the equipment. And then we also created a sim group for doing simulation and simulating our process. So, and they are literally, I'll show you the data structure for these. They're just a whole bunch of data, a bunch of arrays that allow us to pass data in and out of this piece of equipment. Okay, that kind of gets the whole thing. We're going to do a live demo here. We're looking at a pump station, as I mentioned. This pump station has an upstream tank, if you will, and a downstream tank. The pumps automatically start and stop based on the level in the upstream tank. When it gets too high, the pumps start up. We pump water to the downstream tank. And when that upstream tank gets too low, we stop the pumps and away we go. And this is a really simple example of a pump station. Of course, they can get a lot more complicated than this for sure. But I wanted to find something that we could show off. And so real quick, let me switch over to the actual live demo. So this is the SCADA system that's communicating with the Bedrock controller that's sitting here on my bench. And we're simulating all of this data right now, just based on the current conditions and whether a pump's running or not, things like that. Right now we have 1 pump running in manual, and it's flowing somewhere around 2000 GPM and pushing that water from the upstream tank to the downstream tank, basically. Now, on this screen, the thing I wanted to point out here is I talked about these standardized objects. So every analog value you see on this screen is a standard object, whether it's this tank level here or this pressure here, or even this flow that you see here. Those are all just analog instruments. And the beauty of that is this carries to my SCADA system too. So I have a standard pop-up that'll come up on the right-hand side here. That standard pop-up shows me all of the data for this analog instrument. Now, I know what that analog instrument is going to be, no matter what it is. I know all of the properties, and I can create this single pop-up that I can use over and over and over for every object that I pull in. This particular object, I'm using the primary output is GPM, and I'm using a secondary output to show millions of gallons per day, MGD. If we look at the pressure, for instance, I know that the secondary output has been disabled, so I don't display that secondary output on there. We can also take a look at alarms that are enabled on this one. The pressure has 2 highs and 2 lows enabled. I think if we look at the flow based on what's enabled there, if I clicked on it, I must have missed it. There we go. I think the flow is only using, yeah, it has 1 high and 2 lows in this case. And of course, they're all configurable from here. Notice the flow also has an accum to show my accumulator. And as of right now, I've accumulated about 1.2 million gallons today anyway, and close to 12 million for the month. So, and that goes for just about anything. Now, you know, equipment are a little more involved, but there's still some commonality. We have those 4 alarm groups. So if I go to the alarms tab on my pump here, you'll see that I have my 4 groups, my warnings or failure warning, interlock, and not ready. And in this case, I'm only using 4 of the failures. Things are getting slow this morning. 3 warnings. I don't remember how many interlocks. And then my not readies. So this is all common items for my equipment object. I do have a custom section for each piece of equipment, which is this middle section on the settings tab. So this is specific to this pump to allow me to start and stop it, put it in auto or manual, and change the flow for that particular object. So there we go, we shut it down. Now, if I look at a valve, for instance, again, oh, I don't have a valve pop up. I guess I can't show you that. But the valve pop-up would have those same common items, right, that you saw, and then would have a separate custom section in the middle. So, all right, that's probably enough on the SCADA side. Let's dive into some code and talk about how this all comes together. Okay, I'm hoping everybody can see this okay. You're looking at the Bedrock IDE, by the way, for the Bedrock controller. I happen to be connected to what Bedrock calls their OSA remote R20. Bedrockautomation.com, by the way, if you want to go check out their hardware. If you're looking for a secure PLC, they definitely have a great line of PLCs. The OSA Remote R20 is their brick PLC. It has 20 universal IO points. They're all software configurable, which is kind of neat. In any case, that's what I'm connected to, running on my bench here and running this simulation. Now, I've got this laid out, and let me collapse some folders here so we can see this. I try to lay this out logically for myself anyway. So any of my data types, I dump in the data types folder. And then I have a global variables folder where I put all of my global variables that I use in the program. And then I have a program section, which is broken down by basically how I execute them. So I always process the IO first. And then I run that base code that we were talking about. And then I run my process code. So how do I actually control this thing? How do I start and stop pumps, things like that? And then all of the rest of the stuff that I might do. If I have external communications to other PLCs, I'll put that in the COM section. I also have some recipe code that I have in every controller. And that's all standard in mine. And then if I'm doing any simulation, I have a simulation section. And lastly, any system events that I might run. So I might have a on start event, or anytime there's an online change, I might have to initialize some stuff, things like that. So that's kind of how I break up my programs. Now, I also use the POUs section quite a bit, and I don't think Alex really got into that section at all, but that's on the right-hand side of my screen. That POUs section is kind of I'd call it a mini library, just for this particular application. And if you guys haven't realized, you can have multiple devices in your project as well. So I only have one right now, but you can add as many devices as you want. All of those devices have access to this POU section that's on the right-hand side of my screen. That really is handy when you're doing lots of applications that are similar. And I've done specifically that on well sites in the water industry. Every well site is pretty much identical. So I keep all of my code over in the POUs. On the right-hand side are all of my devices and their global variables. And then I just call the same programs over and over for every device. Really, really handy feature. Now, of course, you can also use a library to do the same thing. And Alex talked a little bit about that. So those programs could also be placed in a library, and then you could link to the library in your program as well. Now, in my task manager, the main task is really the big one. I call my main program, which is right here. And then my main program calls all of the underlying programs that I need to run this system. I also run my simulation out of that task. The whole idea of my simulation implementation is I want to simulate the entire thing, first of all, so that we can test everything out, make sure it all works before we go live with an actual process. But my goal with the simulation is to make it really easy to get rid of. And I can get rid of it by simply removing this task and uncommenting that line right there. So I can remove the task, I can uncomment my simulation enable tag, and then the code is ready to go into the field and actually be used for the application itself. So the rest of these tasks are for things like synchronizing the clock. I synchronize with an NTP, network time protocol, to synchronize the clock on the Bedrock automation controller. I also have my symbols task, which was the recipe stuff I was talking about earlier. And then I have a separate COM task if I'm doing any communications outside of the controller. And lastly, by the way, I just started experimenting with visualization, and that's where my visualization task comes in. So that's kind of the layout of the program, if you will, and how I execute those. Now, let's talk a little bit about those data types that I was mentioning in the presentation. So over here, I've got my reusable data types that I use all over the place. And if I go into, say, instruments, in there, we will find a data structure. Now, this data structure really is just a bunch of tags that you throw together. This happens to be the inst A that we're looking at, or analog instrument. And as you can see, pretty typical stuff that you would want from an analog instrument. I always assign a description and a tag number for my devices. And then I have a raw value. This is the value coming from the IO. So when I implement this instrument, these are the two tags that I have to set coming from my end device, whatever that end device happens to be. And as I said, it could be hard IO, it could be some kind of Ethernet connected device or serial connected device. And with an instrument A, it could actually be a calculation too. Back on our screen overview, this flow here is not an actual physical meter. That particular flow is just a sum of the 3 pump meters. But I still create an instrument for it And then I sum those three and pass the data into that particular instrument. So it looks like a real instrument to the rest of the world. So anyway, those are the two that I have to set. Now, if I'm also getting a total value from my end device, if it happens to be a flow meter, then I have another raw value input for that total. Now, the rest of these values are either outputs or inputs for doing things like the calibration hold we talked about. That's my mode input. If it's 0, then it passes the value through. If it's a 1, then it's in manual mode. And the users can set the manual value to tell the object what to output at any particular time. So essentially just puts it in hold and then allows you to change the value if you want to. We have all of our alarms down here. Here's the device fail, device warning. I also have an out of service alarm that I put on every object. And then here's my 6 analog alarms. 3 highs, 3 lows. And then there's also a separate set point deviation. If we happen to be controlling on this particular instrument, maybe it's the pump flow, for instance. And if our flow is deviating from our actual set point, then we can generate an alarm based on that as well. You'll notice that these alarms are another data structure, an alarm analog data structure. And if we just jump over to that real quick, they're pretty simple. Whether it's rising or not, the current value, the set point, and the deadband. Pretty straightforward. That's my my base alarm value, and then my alarm analog, or actually, let me take that back. That's the alarm analog, which extends, didn't plan on getting into this just yet, but I'll talk about it real quick. Notice it extends the alarm base data structure. This is really cool. So I created an alarm base data structure, which has all of the base alarm information. So whether it's enabled or not, the timers for on timers and off timers, if it's active, if it's in alarm, all of that base stuff that comes along with every alarm I created in a structure called alarm base. Then for alarm analog, I created another structure that extends the alarm base, which means it gets all of this stuff that's in the alarm base data structure, and then it adds to it this stuff. So this stuff is specific just for the analog alarm. If I jump over to my digital alarm, it also extends the base, but only adds 2 additional points. The value to evaluate, which is a Boolean in this case because it's digital, and my set point. Does it alarm when it's on or does it alarm when it's off? So these data structures really give you a lot of flexibility in how you can configure them and extend them and use them in lots of different ways. Back to my analog instrument. The rest of these values, curval, by the way, is my output. So essentially when everything's normal, all that happens is this current curval output gets set to the raw val input. So assuming we're in online mode, everything's good quality, then we just take the raw value and we set it to the current value output. That happens to be a structure as well. There's some more stuff associated with the curval. I have min and max values, and I also have units in there for my value. Now the curval 2 is just another output that is typically calculated off of the first output. So if I take a look at the data structure here, you'll see that curval 2 as well as curval 3 have a value, of course. They have a mode. That mode is either disabled or it's one of two calculations. We either do the multiply first or we do the add first. And then here's my two multipliers and offsets. And then lastly, I have a high range, a low range, and engineering units for that particular value. So that allows me to easily add additional units for this particular analog value. And I use this all over the place. We use it in tanks. Typically it comes in feet, but they also want to show gallons, for instance. And this allows me to easily do that and quickly get those unit conversions done. Lastly, we have status codes, and status codes are just used to tell us if something's wrong. And I forget the exact numbers I use. I think I use 128 as a good value. And then less than that means one thing, greater than that means another thing. And accumulators, we didn't talk about that. But every analog value can have up to 5 accumulators. And that's specifically for doing those totalizations going forward. All right, so we're running short on time here, so I'm gonna move along just a little bit. But the other structures are very similar to that. If we take a quick gander at the equipment structure, very similar layout with the exception of, here's my alarm groups. So notice that failure is 10 array, or an array of 10 alarm digitals. And then we have interlock, not ready, and warning. So basically just 40 alarms in groups of 10 that we can use for this piece of equipment. Now, I also put in some standard tags that you would typically see for some kind of equipment. So for instance, if it's in remote, if it's in auto, if it's a valve, we have closed, traveling, and opened. If it's a VFD or a pump, we have a running speed. Position, of course, typically goes with valve, but you could really use those for anything you want. They're just standard data fields that we can use with the equipment. And then we also have standard inputs to this data structure for a close command, open command, run command, things like that. All right, I won't dive into that too much. I should show you the data groups real quick, though. These are the 4 data groups I was talking about in the presentation. So in addition to those standard items, the remote, auto, close, things like that, you also have 4 data groups that are filled with just arrays of data. So if I take a look at my data group here, I broke it up into arrays of 32. So I basically have 6 arrays of 32 booleans, whatever that adds up to. I have some double integers, and then I have some reals. I have what we call switches, which are really just integers, but we typically use them for modes like the hand-off auto switch. That would be an integer, 0, 1, 2, something like that. I also threw in some words because a lot of times we're talking with, Modbus end devices that are passing us word type of data, so we can use that to pass data in. And then every data group has a reset Boolean, which we can use as a reset output to either reset our alarms or reset the device itself, something like that. So really just a whole bunch of data that we can use with this piece of equipment. By the way, for every object that I create, say it's a VFD, I create a spreadsheet that defines what each piece of data in this data group is being used for. And that way I can kind of keep track of things. And on the SCADA side, I actually add descriptions to every piece as well, so that you can see exactly what it's being used for. Okay, how are we doing out there? Hopefully pretty good. Now, let's see how these actually get put together. So I've got these standard objects, right? Inst A, Inst D, equip. Now what I want to do is I want to organize these in kind of a tree in my system. And I do that with these site data types over here on the left. So at the very top, I have my pump station. So I created a structure called station. Now, this station contains 3 pumps, pump 1, 2, and 3. I also have 2 tank levels, tank 1 and 2, suction pressure, discharge pressure, overall flow. And then it has a building object here. I should blow this up a little bit so everybody can see it, huh? That building object is another data structure. If we take a quick gander at that one, that is really building related stuff. So I've got a power meter, got a water on floor instrument, an intrusion, power fail, and my room temperature basically. So I'm kind of building a tree. I have a station. Underneath that, I have pump 1, pump 2, pump 3, which are their own data structures. And then I have building, which has its own data structures. And you can build these out as deep as you want. The beauty of this is when we implement this and we enable our OPC server, it actually shows up as a tree when you browse this object. And I can show you that a little bit later as we dig in. So it really makes organizing this data and bringing this data to your SCADA system really nice and organized in a kind of a tree type fashion. Real quick, let's take a look at our pump structure. Nothing too crazy here. We have 2 pieces of equipment. We have a VFD and we have a valve. And we have 2 analog instruments. We have a flow and a temperature. Now, the next piece is to create a global variable that houses all of this stuff. So a global variable list that houses everything, and it allows me to set all of my default values for all of this stuff. As you can imagine, there's a lot of settings that we have to get in order to take advantage of these standardized structures. You know, a flow instrument is going to look different than a temperature instrument, for instance. So we want to get all those default values set. I do that in a global variable list I call site. So here's my site global variable list. We'll go up to the top here. At the very top, you can see I defined a station, which is my station structure, my station data type. Underneath that, I then define each of the individual objects. So here's tank level, here's tank level 2. And with each of those, I'm assigning the information, the default information that needs to be set. My high range and my low range, all of the different alarms. And as you can see on the tank level 2, I'm using a high and a high. Mid 1 and 2 are disabled. And then I have a low and a low. And I can just set those enabled on and off. Again, these are default values, by the way. So when you first start up, it'll set all of these accordingly. So I just really built out this site global variable list with all of the stuff that needs set up for each type of object. Now, once I've done that, the rest of this gets pretty simple. Back to my main program. Let's close everything else out and kind of clean this up a little bit. So as I said, the main program gets called for my main task. It calls 3 pieces of code. I handle my IO, get all of the IO in from all my different devices. I then run my base code so that I can handle all of that base code for my instruments and equipment. And then lastly, I run my process code, which looks at all of my devices and makes my process decisions and controls all of my objects. So the main IO code is really pretty straightforward. As you can probably guess, I have a bunch of data structures with this as well. But for the Bedrock controller and the way I have this configured, these 2 calls handle all of my hardware IO. So I have 2 slots, 10 channels per slot. So I just call each slot, and all of my IO gets handled. And then all of my data goes into these 2 data structures. If I jump over to my IO global variable list real quick, there you will see my slot 1 and slot 2 and the configuration for each channel. As I mentioned earlier, the Bedrock controller has universal IO on it. So you can see some of these are analog inputs. Some of these are digital inputs. Obviously, if I had outputs, I'd have AOs and DOs as well. So anyway, based on all of these settings, when I call these 2 pieces of code, it goes out and gets all of that IO and sets them in my UDT, or structure, I should say. Now, beyond that, I handle all of my field bus items, whether they be Ethernet IP or Modbus or whatever. And again, I do those with programs. So this happens to be a ProMag 400 flow meter, and I have a special program to call to handle that. So I pass in all the data that's coming from the end device, and then process that data and assign it to a data structure. Now, at the very bottom of this POU, I should mention to everyone, I really like structured text. There's no reason you couldn't write this code in function block diagram or CFC or whatever flavor you like. I'm partial to structured text, mostly because of my background in programming, but you could really write this code in any language. I auto-generate a lot of this code, and I use Excel a lot to do that. And structured text really works well with that. I can copy and paste really easy. So anyway, at the very bottom here, I call this map.io, and map.io is kind of a sub-program of my main IO. It's actually called an action. So in any program, you can add an action. You can also add properties, methods, and transition. I use the actions a lot. It's just a way to kind of break up my code a little bit. But if I jump over to that map.io, this is where I'm taking the hard IO and mapping that to an instrument. So at the very top, my tank level is coming in on slot 1, channel 1. So I call a piece of code called map inst A from IO. I pass it the instrument or the data structure for my analog instrument, and I pass it the IO point that data is coming from. That's going to take my IO point and assign my raw values for that instrument. So let's just jump over that code real quick and take a look at it. So we'll go to browse, go to definition. So notice this is just a program. It's not a function block. It's simply a program that has 2 var in out variables in it. Now, a var in out passes a reference to that object. So there's really no memory getting taken up in this program. It's really just a reference to that object. Same with the IO point. So now I can act on that variable that got passed in and do whatever I want with it. So for instance, I take my raw value and I set it equal to my engineering unit value that's coming from my IO in this case. I also set my raw value status as well when I run this. And then the rest of this is actually just for simulation, so that I can simulate this tag when I'm in a simulation environment. So pretty straightforward. You simply run all of your IO, and then you call these programs to handle mapping that IO to individual items inside of that structure. And I do that over and over and over. For my pump, these VFDs are, they're Eaton SVX 9000s, and I know what kind of data is coming from those. So again, I call a program, I pass my data structure into that program, and I pass the IO that's coming from my actual IO. And then of course, inside that program, all I'm doing is mapping data in. Jump into that real quick. And you can see, I'm using that raw data group that we talked about earlier. And I'm setting the values that are coming from my IO. And now I know when I run my common code or my base code for this piece of equipment, I know that running is always going to be on this raw input here. All right, now let's jump to the next section, which is base code. And then we'll take a quick look at the process code, and then we'll kind of wrap things up. So the base code, if you remember back in my main program, I first called main IO. So that handled all that IO and it mapped all the IO to my instruments. Now I run my base code. So under the main base code program, again, I've broken this up a little bit. I run base code for the station. I run base code for each of the pumps, and then I run base code for the building. And those are all defined in these subs here. Let's take a quick look at the pump. These are really straightforward. Again, I'm calling another program and passing in my data structure. So the pump itself, by the way, is an equipment object. And then the VFD, which is under the pump, is equipment object, and the valve is an equipment object. Lastly, I have one instrument, which is the flow for the pump. So I call my instrument code for that. Let's take a look at that instrument code, just so you guys get an idea of what's going on here. Remember that this is an analog instrument. So all I'm going to do in this code is grab my raw value, and based on the settings, I'm going to pass that raw value to the curval, the output. And actually I pass it to a temporary value first. And then I look for my clamping and things like that. And ultimately I will set that curval. If we can find that part somewhere down here. There we go, right there. Finally, at some point in the code, right, I set the value or the output value in my current value for this particular instrument. And there's a lot of other stuff going on there. I'm looking for whether it's in calibration hold or not. I'm also calculating an average value, which I use a lot, by the way. So this particular task here is looking at the value once a second, and it's filling a buffer of 60. And then I average that buffer. So I get a 1 minute rolling average for this particular value, which when you have really, loud, nasty data, that average value can come in really handy at times. I also do a percent value on every object. So that's what that's doing. I have a min and a max, which the operator can reset as well. So all of this standard stuff happens on every single analog instrument. And once I've set this all up and tested it, all I have to do, again, in my base code is call that code, pass in my data structure, and it's taken care of. So adding analog instruments is really straightforward. By the way, it's handling all the alarms as well. So all of the alarm code is in that, that instrument code as well. All right, so that's the base code. Now, the equipment base code is actually pretty simple. Really, all we're doing in here is alarms. So we handle our 40 alarms. And then at the bottom, we handle our statistics. So our run times, out of service, and available equipment statistics, if you will. And that's all there is to the base code on the equipment. Equipment is really all about the process code and how we're controlling that piece of equipment. Okay, so we jump back to main. We've talked about the IO handling, talked about the base code. Lastly, of course, is the process. So if I jump to the process now, remember that I have now set up all of these standard objects. And my goal is in the process code to only use those standard objects for anything that I'm using in there. So I'm not referencing any hard IO anywhere in my process code. Now I actually broke this down. So I call main process, and all that does is call my pump station process. But if we take a look at this, this is where I'm making process decisions. So for instance, if my tank level mid-2 alarm is active, that means, hey, it's time to run my pumps. So if that turns on, then I set my run command true on my 3 pumps. If mid-1 is active, that means that the tank is reaching its bottom. So I turn my run commands off. Pretty straightforward, right? If they take the entire station out of auto, then I always turn my run commands off to my pumps and shut them off, regardless of the tank level at any time. And then I run process code for my individual pumps. And all 3 pumps are identical. So I'll just create a single program, call that program, and pass in my pump data structure. And we'll take a look at that in a second. Lastly, I do some station level stuff. So is the station itself running? And that's just simply if any one of the 3 pumps is running, then the station itself is running. The station is an equipment object itself. So that way we get statistics on the station, on the entire station runtime, and availability if we want it as well. And then, by the way, the flow low alarms are only enabled if the station is running. So I put that to use there to enable and disable my flow alarms on the station itself. Now, if we look at the pump code, this is what actually starts and stops the pump. And of course, the pump has all kinds of settings as to whether it's in auto, if we have a remote signal from it, things like that. But all in all, it's not too bad. I get the data from the object up above and set my running, my remote, and my auto. Again, flow alarms are enabled based on whether it's running or not. And then here's my run command. So this is where I'm looking at that run command that we set in the previous program we looked at. And based on whether we're in auto or not, we set another tag, which is one of our generic data group tags, to true or false. And then down below, I use that later on to actually call my VFD itself. And inside that VFD code, I determine whether the VFD is ready or not, and actually send it a run command or not, based on that VFD. Same with the valve. The valve gets a variable that I set to tell it to either open or close. And then I call a process POU for that valve to handle it. So everything's structured. We're calling these programs and passing values as var in outs, and handling those. I hope I've explained that part well. And great timing, Tom. So that is one thing I wanted to talk about with troubleshooting this type of program. With function blocks, it's actually pretty easy to program a function block because you can open that instance of function block and actually see all the data. With a POU like this, where we're passing an in-out value, the value that you're going to see in this program is the last one that was called in your program for this particular program. So you're only going to see the data for the last one that was called, and that can get confusing. So let's go online real quick and take a look at how this looks. Let's clean everything up again, and we'll log in and get online with this. Now, let's say that I want to troubleshoot pump one, for instance. I want to look at what's going on in pump one. The actual easiest way to do it is to go to the site. Notice I get a beautiful tree, by the way, and that's because I've organized these data structures. So I can expand out my station. I can expand out pump one. And then I want to look specifically at the VFD. So I'll expand out the VFD. And now I'm looking at the data for that VFD. And this is where I spend most of my time troubleshooting, by the way, because I can see all of the data. I can see what's going on and try to figure things out. Now, if I actually have to look at the code, let's go to our process pump VFD code, which calls a bunch of other code, by the way. So let's go to the actual control here. Now, the problem we're going to run into here is the data I'm looking at right now is probably not pump one. If I jump back over here and look at this piece of equipment, look at that. I'm looking at pump three, and I'm looking at pump three because in my process code, that is the last one that I called in my code. So this might sound a little weird, but what I will often do if I need to troubleshoot pump one, I'll move it to the bottom, jump back into runtime, and I can do a quick online change without affecting anything. And now when I jump back into runtime, I will actually be looking at pump one. So if I go back to my process pump VFD, I am now looking at my pump one VFD, and all of the data that I see here in my code is for pump one, and I can troubleshoot it. Now, I honestly don't find myself having to do that very often because I simulate everything. I test it all on the bench, and I test it with only one program running. And I can comment out the other stuff. So I often get all of this troubleshooting done up front, and then in the field, it's all about getting the IO hooked up and testing it all out. So that's where simulation becomes so powerful, by the way, to get all of this tested out and running. I often even make it available to operators so they can look at it, see the screens, operate the plant, and get feedback that way as well. I can't speak highly enough about simulating your code and testing it without somebody standing over your shoulder, right? Going, is it done yet? Is it done yet? That really, really comes in handy. So thanks for that question, Tom, by the way. You know, guys, the whole goal of me here is to not, I wasn't planning to tell you, hey, this is the only way to do object-oriented programming, because it absolutely is not. This is one method that I found that I really like, and it has worked well for my applications. So my goal here, though, was to just kind of give you guys an idea of how flexible this code is, and how you can use CODESYS in many different ways to accomplish what you're looking for. And there's lots of tools in here and lots of ways to implement this stuff. And that was really my end goal. And I kind of feel like I've really gone over here, so we won't extend this anymore, but hopefully you guys got something out of that.